webinar. I'm pleased that you join us today to learn more about how to think about carbon dioxide as a raw material for products that can help to counter climate change effects. My name is Volker Sick, and I serve as the Director of the Global CO2 Initiative at the University of Michigan. The mission of the initiative is to have carbon capture and utilization recognized and implemented as a mainstream climate solution that is financially sustainable. It is amazing to look at what we can actually do with carbon dioxide as a feedstock. Not only can we make materials, chemicals, even fuels that currently are produced with fossil carbon, and therefore we remove the introduction of new CO2 into the atmosphere. It is also possible to use CO2 to make entirely new products, such as building materials that permanently remove CO2 from the atmosphere. Such materials can therefore help to reduce the enormous amount of excess CO2 in the atmosphere to help stabilize the climate. Today, we will discuss fundamental aspects of carbon capture and utilization, with a strong emphasis on how to measure and evaluate success. I am pleased to introduce experts from our partners at the Institute for Advanced Sustainability Studies in Potsdam, RWTH Aachen, the University of Sheffield, and TU Berlin. And Dr. Lorenzo Cremonese from IASS will take it from here.
Thank you, Volker, for your nice introduction, and a very warm welcome to all the attendees in our webinar today. My name is Lorenzo Cremonese, and I work at the Institute for Advanced Sustainability Studies in Potsdam, Germany, in the group of CO2 utilization strategies and society. And I'm also a member of the Consistent project. So on your screen, you should see the event of today and the agenda. We're going to have 3 sessions. We're going to present 3 different presentations and a break and a post session in between. So moving to my presentation. So today I'm glad to present the protagonist of today, that is carbon dioxide. We all know more or less the problems, the challenges that these tiny molecules is creating to our societies. This is why today we would like to look at it from a different perspective. That is, first of all, why we need carbon dioxide in the first place on our planet, and why so many processes that we run nowadays produce CO2 and then we emit to the atmosphere. So couldn't we just stop these processes and stop emitting carbon dioxide to the atmosphere? So in other words, what is the big deal about carbon dioxide? To answer these and other questions, we'll go together through a short journey where we're gonna get to know a little bit better the what, the why, and the how of CO2, and also put this in relation with the topic of energy, emissions, and climate. But before starting today, we would like to get a little bit more familiar with the attendees that connected to us today, and that's why we would like to run a short sort of ice-breaking session to understand your background, but also your interest for the meeting today. This will also help us to steer our presentations towards your interests. For this reason, we would like to ask you a couple of questions first, and please feel free to answer in the chat. The first question we'd like to address to you is, why are you with us today? What aspect of the topic of CO2 reutilization do you find more interesting that made you click on the login button? So please feel free to answer in the chat. I will shortly stop sharing to the better view. And maybe we can also run the second question, that is, what do you expect to learn from our presentation today? Do you have any expectation in particular? So we would like to know from you, in case you have any special interest or any special question about your expectation today, to maybe share it with us in the chat. So let's see if we get any insights from. Right, the first comment is interest on CO2 mineralization. It's a very interesting topic and also very advanced technologically, comparison to others. I'll let you know. Another comment is about the efficiency of CO2 capturing. That I'm not addressing my presentation. Maybe my colleagues who can say something about that later. Development. Okay, developments in general, CCU. Okay, and I also take the occasion to remind to you all, please feel free to write already your questions in the chat during our presentations. And time permitting, we will discuss this question and answer them at the very end of this meeting today. Carbon negative technologies is another topic that appeared in the chat. And we're gonna go quickly through those. And circular economy, I will shortly introduce the concept of circular economy applied to CO2. Okay, so thank you very much. I will share my screen again now. And we will start with the presentation, the first one for today. Okay, so let's start from the very beginning, from the origin, and from the concept of energy. We all know how important energy is for our daily life, but also for our societies, for our activities, but also for ourselves. I mean, if we don't have enough energy, we're going to have a hard day. So energy is quite a central topic for our society, but also for our personal existence. Where does the energy come from? So what is the primary energy pool where we as humans can take energy from? This is clearly the sun. This huge sphere of hydrogen and helium that through nuclear reaction emits the precious electromagnetic waves that traveling through the universe reach our planet. And we all like and enjoy. We know them as sun rays. So today, the expansion of renewable energies that we observe worldwide, such as photovoltaic panels, such as wind turbine, but also concentrating solar plants, just to name a few, are a clear attempt to catch this energy and accumulate it for satisfying mankind's activities. Are these the most sophisticated advanced technologies to collect and store the energy of the sun? Probably not, as there is another way to fulfill this job. The most clever technology is in fact nature. Yes, this process called photosynthesis is the best way to store the energy from the sun and exists for much, much longer than the first human, the first man put his foot on this planet, more than 3 billion years ago. Plants are able to transform electromagnetic energy into chemical energy as glucose. It is estimated that each year about 150 gigatons of CO2 are fixed by terrestrial organisms on our planet and 120 gigatons by marine organisms. To put this into perspective, the man-made CO2 emissions only reach about 10 gigatons per year. So we therefore understand there are two main ways to collect energy. One is about catching the nowadays solar energy by renewable technologies, while the other is exploiting not the sun rays of today, but what we can call the sun rays of the past, a sort of fossil sun that we all commonly know as fossil carbon. So coal, oil, and gas stored for millions of years in the deep layers of the Earth's crust. The second option that we just named is the one that had been mainly perpetrated for about 3 centuries, as it was so far the easiest way to produce energy. We just dig it, burn it, and get the energy out of it. There is no other natural pool of energy on Earth that is comparable to biological fossil carbon in terms of geography, availability, amount, and convenience of utilization without evident catastrophic consequences. Like, for example, it did happen with the nuclear energy, for example. But what are the downsides of using this fossil material to produce energy? So fossil carbon is carbon mostly bound to hydrogen in more complex organic compounds. When we burn it, carbon dioxide and water are produced through reaction of organic material with atmospheric oxygen, and the chemical energy trapped in these substances is released. More specifically, the energy release is equal to the difference that we see between these two energy levels, E2 and E1 in the figure. The new compound called CO2, carbon dioxide, has some interesting characteristics. First of all, its geometry. It's a linear molecule, and this means it is released in the form of a gas and that can accumulate in the atmosphere. The second characteristic important for us is that it is a gas, and it's the gas that has the capacity to trap some of the sun energy, vibrate, and release part of this energy as infrared rays or heat, if you will, warming up the atmosphere. to the temperature that we have nowadays on the planet. So this effect occurs in large scale in the atmosphere. The sun ray, it gets gases such as CO2, but also water, methane, and others, warming up the atmosphere to the temperature we observe today. Just consider that without this effect, the average atmospheric temperature of the Earth would be around -18 degrees Celsius, not really the best place where to live. This process is called greenhouse effect, and gases like CO2, greenhouse gases. Why they're called like this? Because this process really resembles the one occurring in the greenhouses that we use to grow, for example, tomatoes during cold seasons. The air underneath the greenhouse gets warmed up by the sun rays passing through the glass, but the physical barrier prevents it to escape, so the temperature inside the greenhouse increases. So if you will, you can imagine the Earth as placed and trapped into a huge greenhouse where the CO2 concentration increases year by year. It is then relatively clear that the more CO2 is added to the atmosphere, the warmer the atmosphere will turn. So it is also important to say that carbon dioxide was always present in the atmosphere in the geological periods of our planet, as we can see in the figure on the left-hand side here. We covered the last 800,000 years, and scientific evidences actually tell us that this concentration is rising extremely quickly now if compared to past geological trends, as we can see in the peak on the right extreme of the figure. While we are talking, in fact, more and more fossil sun, as we called it, energy, fossil energy, is digged out and burned, increasing second after second the concentration of atmospheric carbon. As expected, the increased CO2 concentration is also triggering a fast raise of average worldwide temperature, as we can see in the figures on the right in the animation. This shows the temperature increase for the last 170 years, but also show how quickly we are reaching the 1.5 degrees above pre-industrial levels. There is still some skepticism around the topic of climate change. And some questions are raised, for example, is this temperature increase that we are seeing today really due to human activities? Or is it a natural trend that the Earth is going through caused by other factors, such as, for example, change of the planet orbit, sun irradiation, volcanoes activities, and so on? In this diagram, scientists decouple natural forcing causing global warming from human forcing. And what we see is that the calculated temperature variation described by the red line very well resembles the observed temperature variation, while the expected temperature changes modeled without factoring in human influences show a very different trend. So adaptation to a changing climate as the one we experience today, and that this rate of development is clearly unsustainable for modern societies. It is not only about average temperature, but also about peak temperature, a specific location, change of time and the entity of rain season, for example, humidity, and similar. All of these create a multitude of consequences for societies. Decrease or loss of food production, droughts, soil degradation, coast erosions, melting glaciers and Arctic, and rising of sea levels, but also, for example, increase of extreme weather conditions like tornadoes. All of this can potentially lead to poverty, famine, large migration, and ultimately to death. So what are we doing to prevent this, to slow this down? Governments from all over the world are trying to curb emission by substitution of fossil carbon with renewables, by increasing also efficiency, reducing energy demands, and so on. The effect of these efforts are evident, but far to be enough, unfortunately. Temperatures are increasing faster and faster, and tipping points like the 2-degree target set by the Paris Agreement at COP25 are getting closer, according to the most accredited future models. So there is a question here. Is there any additional solution we can embrace that can help us to slow down this trend and keep the planet under the same shape and condition that we observe today? So there are several ways to reduce atmospheric carbon dioxide, and I report here 3 of them. The first one is very easy to understand, is just to plant more trees. Unfortunately, because of the vast fires, spreading of desertification, and climate change itself, what we are observing today is rather deforestation instead of afforestation. Another solution is related to soil carbon, that is about enhancing carbon concentration in soils. In fact, a very large amount of carbon can be stored in soils, But unfortunately, due to several reasons like expansion of monoculture, deforestation, large use of pesticides, we observe a worldwide impoverishment of soil carbons. Researchers are also proposing another way to sequestrate atmospheric carbon dioxide by a process called enhanced weathering that consists of inducing a reaction between atmospheric CO2 and some rocks such as carbonates and silicates. The solution has nevertheless still limitations, as transport and grounding of rocks can be very expensive, and also the induced pH changes that would happen in areas where this reaction takes place can have relevant downsides. So now we can move to the core of our presentation, that is, if we cannot avoid more carbon, to emit more carbon to the atmosphere, if we can't really decrease it at a level that we would like to, can we maybe catch and reuse these molecules following, for example, the concept of recycling that we all know much better when we relate to common goods, like, for example, plastic and paper? Many of you have probably already heard about circular economy that requires that the entire value chain of a product is reshaped in a way that its production and use allow it to be reused at the end of its life. This relatively new approach is in contrast with the linear life cycle pathway that we all know and that still characterize most of our products today. And that sees that these goods and these products to becoming a waste at the end of the life, something that is not useful anymore and that it has to be disposed of. So the three pillars of circular economy are reduce, reuse, and recycle that we can also apply to carbon dioxide. So reduce its production first, reuse it once produced, and recycle it through transforming it to something else that is useful for our daily life. The idea of applying this concept to CO2 or reusing it instead of just emitting it to the atmosphere leads to a change of perspective. That is basically looking at CO2 not as a waste anymore, but as an asset, as a potentially important resource. And this leads me to the last slide for my presentation today. That is that under this overarching idea, in the last decade, we've seen the development of carbon capture and utilization technologies, also called CCU. How would the reuse of carbon dioxide look like in practice? As we can see in this nice image produced by the Nova Institute, renewable power can be used directly by several sectors, as industry, for example, or can also be used to produce hydrogen. Hydrogen is then hydrogen then reacts with compounds such as CO2, produced also, or a carbon material produced by biomass and so on, and also needing also additional energy that may be at the base of the production of several goods, such as chemical, plastic, like for example, methanol or similar, but also fuels. And these fuels could help to decarbonize sectors like, for example, road transport or aviation by synthetic kerosene. In fact, we've seen lately then road transport and aviation are two sectors that are very challenging to be decarbonized. So my presentation finishes here today. My colleagues after me will expand on the topic of CO2 utilization technology in the next presentation. From my side, I'd like to thank you for your attention, and I hope that you're enjoying the event until now. So now I would like to give the floor to my colleague, Tim Langerhorst from the University of Aachen and the ETH Zurich for the next presentation. So thanks again, and Tim, the floor is yours.
Yeah, thank you, Lorenzo, for this introduction of our CO2 molecule that is in focus of our talk today. Lorenzo already told us that that CO2 might be a good option to renew our chemical sector, for example. And he already explained shortly the most important drawback that we have to deal with. And I'd like to start with this drawback and then explain based on this why it's so important to have a very in-depth look on each technology and all the assumptions we make when we figure out if CO2 utilization is really a good idea. And by this, I'm explaining you the methodology of life cycle assessment. But let's come to this later on. So first, as already explained by Lorenzo, we have to inverse the combustion to get something valuable out of CO2, because CO2 is already the product of combustion. And what you see here in this video is something that is built from inverse combustion. And we all know that this does not really happen in our lives, because there's much energy that comes from combustion, and we have to put all this energy back inside our CO2 molecules to get something of more structure and more value out of it. So we all know this does not happen, as you see here in the video, but vice versa. And you might remember this slide from Lorenzo. I just added that we have to put all this energy in to get something new out of CO2. And this is the most important drawback we have when talking about CO2 utilization. So we come to the question if it's really a good idea to do so. On the one hand, we have the recycling idea and the idea of circular economy, and that's a very good idea. However, maybe it's not applicable to CO2 because of this high energy demand we have to get something valuable out of it. So we are not the only ones that think about it a lot and try to figure out if it's a good idea. What you see here are many different newspaper articles you might have seen the last years, and also articles in scientific journals. And all of them are discussing if it's good or if it's bad, and come to different conclusions. But why are these conclusions so differently? That was the main reason why we formed as a group and wanted to have a more in-depth look on how to assess for those technologies. And Lorenzo will talk to you later and explain what we did to reach this. And I will now explain you the most important things you need to know for this when talking about life cycle assessment. So what comes in our minds at the very first stage is, what does environmentally, for example, beneficial really mean for us? And for all of you, there might be different ideas in your minds. For example, some might know that it will only happen if it's financial beneficial as well. For others, it might be more important to have a look on the oceans or on trees, animals, global forests, global warming, and all these different categories. And how should we now put all of this together in one easy answer to say yes or no for CCU? So it's not that easy to just say yes or no, and it really depends on all these assumptions you make and how you evaluate every single factor on your own. And for this, we have already a well-established tool, which is called life cycle assessment. Now I'm going to explain a bit more about it. So first, we need to know that life cycle assessment is a holistic method. It covers all these different environmental impacts in different, we call it categories, impact categories. For example, as you see here in the icons, global warming impact, or the use of fossil resources, human health influences, acid rain, and even our land use. And all these aspects are discussed on a full product life cycle scale. So we look at the whole value chain of each product that we assess. And so we do it for CO2 as well. I will show it a little bit more about it on the next slides. So as I already said, it's a well-established tool, this life cycle assessment, and it's also fixed in ISO standards, and we apply it since the 1990s. So there are 4 different phases which LCA consists. The first is the goal and scope definition, and we already talked about it. So today we are focusing on CO2-based products, and we brought you the example of CO2-based methanol. We will discuss on the next page. And we already said that there are different impact categories we have to care about, and all this is set in the goal and scope definition. And the next step is the life cycle inventory, and this is all about collecting all the data we need to answer the questions we have at the beginning. Let's have a more detailed look on this, because there's many to learn about. So, as I said, we will have a closer look on the use of methanol. And methanol can be used in the chemical industry as a feedstock, so a very basic chemical that can be used for many different chemicals that can be made out of it. However, some people think, okay, maybe if we can make it out of CO2, it's a good idea to burn it in our cars to have a carbon neutral fuel. And we will discuss this a little bit while having a closer look on the whole life cycle. So in LCA, we do not only look at the use phase, but have to look at the whole value chain, as I already said. And for methanol, this is the feedstocks. Where do the feedstocks come from? And the synthesis of methanol in the next, and we have to concentrate and purify it to have it in in a useful way at the end. And all this is combined with transport, because there are different places we have to bring methanol to. For us, as we are talking about CO2 utilization, the very first step is very important, because we have to capture the CO2, and this is different from other feedstocks. And as I already told you, we have to get a lot of energy. For example, we get this energy inside the molecule CO2, or combine a low energy CO2 with a high energy H2 hydrogen to get something more valuable out of it via chemical reaction. And this hydrogen also needs a lot of energy. And here you see all these stages, energy is needed. And energy can come from different sources. We have renewable sources, and we have those conventional old sources we used. Lorenzo already explained from fossil resources. So now you notice that it depends on which energy we use for our technology, because using renewables gets us a lower impact at the end. However, if we still use these energy sources with a low impact, we still have the impact of burning the fuel at the end, as you see here. So it still might not be a good idea to burn it, but to use it for different cases. The next stages, just to summarize, this is called the within the factory gates. This step is distribution and transport, and you might remember them from the full life cycle. And we also have the disposal phase at the end, and this depends on what we use our methanol for. And we do not only want to assess this on its own, but we have to make decisions out of our assessment. And therefore, we need different things we can refer to and compare it to. And this can be, for example, if we're going to burn it, we can compare it with burning money, burning woods, and burning, for example, methanol that comes from fossil resources. And as you already see burning money won't be a good idea. However, burning methanol might not be an option as well. So, oh, sorry. When burning things or using it differently, we have to talk about what is the purpose. Why are we going to burn it? And this purpose we figure out as the functional unit. If we are going to burn it, our functional unit might be the energy content, because we want to know how much energy can we get from burning. However, now we talked so much about that burning might not be the best option for methanol. So let's apply a different functional unit here. We will now apply 1 kilogram of methanol and compare it with 1 kilogram of methanol that is made from fossil resources, and stop the thinking about burning it, because it won't help us to reach climate neutrality. And from all these stages, we collect all the data we need, and now it's a simple step to translate the data we already gathered here to euros or dollars, to make a techno-economical assessment, which is quite the same as life cycle assessment, but focused on how to get money out of it, and for sure our environmental impacts. So if we're going to compare dollars with euros, we can simply apply the actual currency and see that we can make one value out of it, and just get, for example, euros out of it. However, this does not apply for the different impact categories we're talking about, because we can't say that that 1 degree in global warming is like that much of euros. This doesn't apply. So we have to talk about this separately and discuss this separately, as you see here. So now you have an overview of how life cycle assessment applies to different stages. And we did this for a lot of different technologies that were already assessed, and we had an overview of all these studies and wanted to compare them to come to the right result, which of the technologies to produce methanol might be the best option. What you see here, each color represents one technology, and if there's more than just one bar, this means that there are different studies that come to different results. For example, if you see here the blue bars, some say it's even better than the conventional one you see here as a gray line. However, other studies come to completely opposite conclusions. And why is this? And about this, you will learn more in the talk of Stephen. But before that, Lorenzo.
Thank you very much, Tim. Thanks a lot. And yeah, we just have to have a very short break, only 2 minutes, just to grab a coffee or check your emails and give you a little bit of freedom before we move to the next session. That please reconvene with us in maximum 2 minutes from now. We're going to have some polls. We're going to run a poll section with some question and answers. So see you in a bit. Volker, maybe I can ask you already to get ready for the next session. Thanks. We're gonna start in less than a minute.
I'm ready.
Great. Okay, so 2 minutes passed on my clock. So what we're gonna do now, we're gonna have 5 questions for the audience today. You should be able anytime soon to see the first question appearing on the screen, and you should be able to answer. There are 4 possible answers, so please answer, and then we can discuss together the results. Right, the first question says, which one is the largest carbon reservoir among the following options? First one is atmosphere, then ocean, soil, and biosphere. Okay, do they need to reply to all the questions? We can move one by one.
I see the whole collection. I had assumed it would be one by one, but it seems that they have to reply to all of them in sequence.
Okay, then that's fine. Please do that. Second question is, what is the share of emissions produced by fossil fuels combustion among all anthropogenic emissions? The different answers are 20%, 40%, 60% to 80%. Third question is, how many CCU plants are under development or are in operation in Europe, excluding urea production? We exclude urea production because it's already an established technology, is already happening today. Possible answers are a few, between 10 and 20, about 50, or more than 50. Fourth question is, roughly how many times do you have to use a cotton bag before it has a lower global warming potential than a single-use plastic bag? Possible answer are between 13 till 195, so please choose yours. The last question is about the profitability of CCU technologies. Does it depend on which one of these parameters? CO2 price, meaning CO2 has to be bought on the market for the actor that wants to use it. Market price of the final product, cost of production, or all of these factors. So we're going to see soon the answers to this question, and we will comment them briefly. Okay, I guess you have the control now for the answer.
We have about half of the attendees who have entered
their
answers.
Then maybe we wait
another half minute to give others the chance to add their evaluation.
Sure. We might have lost a few attendees for a longer break. I hope not.
No. As many are as were before the break. So I'm ending the poll now. We have 32 responses. And here we go. I'm sharing the results. Great. So Lorenzo, responses?
Sure. So let's start from the first question. So the answer that collected more preferences, about 45%, is the correct one, is the ocean. The ocean is the biggest reservoir of CO2 among the one that we present in the answers. So the ocean is about 40,000 gigatons of carbon dissolved normally as carbonate, and this is equivalent to about 6 million blue whales, right? So it's definitely the correct answer. The second one was, what is the share of emission produced by fossil fuel combustion among all anthropogenic emissions? And here we see the two answers got exactly the same votes, 36%, 40 and 60%. And I have to say the correct one is the third one, is 60%, or a little bit higher than 60% actually. And the remaining emissions are mainly from deforestation, fertilization, livestock, and change of use. There are also many other processes that produce CO2, natural processes that have about 60% of the total, like, for example, volcanoes, but also some other processes like melting of, or better release of methane from methanhydrates to the melting of the permafrost. Let's move to the third question. How many CCU plants are under development or in operation in Europe nowadays? Between 10 and 20, and got 55% of preferences is the correct one. It's definitely the correct one. We counted about 15, 14. And for example, one that is relatively known in the field is the plant run by Carbon8 in the UK. That is not properly Europe, if you will, but they're also operating in the Netherlands, and with the new plant that is under construction. Here, what Carbon8 is a license or a patent for utilizing construction, so to produce construction material from waste, combining with CO2. And the last question was, no, the question number 4, sorry. How many times do you have to use a cotton bag before it has a lower climate warming potential than a single-use plastic bag? So the answer from our attendees, the most preferred one is the third. So 39% of people replied this 130 times, and is actually the correct one. So we need to use that 130 times at least in order to be preferable from a climate perspective to a plastic bag. Although there is a new study, a Danish new study, that looks not only at the climate perspective, but at the environmental, so a broader perspective, and numbers are much, much higher. I wrote down here some numbers, and it seems like that for a paper bag would be 3 times, bag for life 4 times, heavy duty plastic time 12 times, sorry, these were the one for the answers, while if we look at Danish, the Danish study, seems like that it should be used about 7,100 times more for a cotton bag and 20 times for an organic cotton bag. So this is just to remind the complexity of CCU and how important it is to run a proper LCA to understand what is really convenient for a climate, for environmental perspective. And the last question is about the profitability of a given CCU technology. It depends of which one of these 3 factors, or all of them, and actually the correct answer that has been chosen by 88% of our attendees is the correct one, all of them, because basically all of them participate to the total cost or to the revenues that we can achieve from a certain CCU technology or product. So thank you very much for all the people that engaged with us in this interesting questionnaire. And we can move now to the last presentation from my colleague Stephen McCord from the University of Sheffield, that we talk more about our consistent project and what we do in our daily activities related to CCU. So Stephen, the floor is yours.
Hi, thanks Lorenzo. Yeah, so just sort of looking at the diagram that we have on stage that Tim finished with, you can see there that there are lots of different ways that we can use CO2, lots of different products, as we've spoken about, and there are ways of sort of measuring how impactful this is in terms of the environment, and whether you can sort of make any money out of it as well. So other things that people may be bothered about. So as Tim pointed out with his last slide, there are multiple assessments that are already out there around the environmental impact of some of these CCU products like methanol. It's a little bit worrying, I suppose, to see such a variance in terms of the actual results from those studies, and that kind of suggests that maybe that we need a little bit more help in making those studies. So we are our project really, and we're going to focus more on this talk about why we do what we do rather than what we do. So should you have more interest in that, we are happy to tell you more about that. But yeah, so our project is here to maybe help people fine-tune those studies a little bit. So let's think about what issues may be for stakeholders. So by stakeholders, we mean anyone who has an interest here in CCU, what sort of issues they may have for the application of these types of studies for studies on economics and the environmental impact. So we have three main ones. The first one being, how do you know if a study is any good? So someone presents you a study, it's got lots of numbers, excellent. I have no idea if that's better or worse than what a study that anyone else has done. How do we deal with a lack of transparency? So this time, let's imagine that someone doesn't even present you a study, they just tell you, oh, this is 20% better than the products that you'll find on the market. So my methanol, sort of following Tim's example, has much less impact than the methanol of everybody else's. And finally, how can we compare between studies? So this is a particular interest, I suppose, if you're interested in CCU, because if we're going to move away from these technologies that we've already established, we want to know that they are actually better. And if we want to invest money into growing the technologies that help us fight climate change the best, or limit those impacts the best, and we have a limited amount of money, we want to find the best and most promising technologies to invest in. So in other words, how can we make sure that we compare apples to apples and not apples to oranges, for example? So let's take a different type of example and talk about transparency. So a real simple one here. There was an advert last year for Europe's lowest emissions and lowest fares airline. How long do you think this advert was allowed to run for before it ran into problems? About a month is the answer. So Ryanair had an advert that was banned relatively quickly for its misleading environmental claims. So if you remember, they come to be the lowest cost and lowest emitting airline in Europe. However, when you actually looked at what they meant by low emissions and the text advert they have, so the print advert claimed they had the lowest carbon emissions of any major airline, what that really meant was that they had less than the average, and actually the statistics it used only included 4 airlines, and the data was from 2011. So here we can see possibly there is actually there is a study that's been conducted. Maybe this study has been conducted to the relevant standard, but the conclusions of that study are maybe not so in line with the conclusions that are portrayed in the advert. So how do we solve this problem? How can we ensure that people run these environmental studies, especially things like life cycle assessments, in a way that is more optimal and more uniform? Luckily, lots of people have already worked on this and have developed what's called an ISO standard. So this is an international standard. So what is an ISO for those of you that aren't familiar? Well, this is how they explain their whole organization themselves. So this is a formula that best describes the way of doing something. So great, we have one for life cycle assessment, problem solved. Yeah, maybe not. There is one problem that still persists, in that the ISO is very comprehensive, but it's also very broad in terms of what it allows you to do. So to explain this in sort of maybe a little bit more accessible language, let's take an example. But before we do that, let's just keep in mind the graph that Tim showed before, where we can see all these different variations in the outputs of these studies. So going back to our example, why would we want more specific guidelines for CCU? Well, let's take an example being cake, and let's write an ISO standard for what we call a cake. So we want something that is general in terms of its guidance and its content and the methodology. So we're going to say that a cake should contain flour, it should contain eggs and fat and sugar. Great. We say it should be baked in the oven. So that's our method. And then we give some optional elements. So we can say we can flavor it with things like fruits or nuts or other ingredients like chocolate as well. So this still leaves open a lot of our methodological choices, similar to our actual ISO for LCA. So we don't answer how many eggs people need and whether they just need the whites or the yolks as well. We don't specify an oven temperature or for how long we need to bake this cake. And we don't specify things like types of flour and sugar. So we've given people a general method that they can follow, which is very useful. You know, it's very useful. Now we have something to work on, but we can still end up with a range of different cakes. And that can be quite problematic to then sort of compare between the different types, say which cake is best, which cake is most suitable for me, for whatever I want. So all of these options are ISO compliant. So how do we ensure that we get results that are comparable? So if the aim of our work, if our whole goal is to be able to compare and identify what's best, maybe the trick is to close some of these methodological choices. So in our example, what we're going to do is we're going to close this and maybe focus more on directing people to make carrot cake. Because now the challenge changes a little bit, and now we have to identify what are the best methodological choices for our specific needs. So if we want people to make carrot cakes, then yeah, how do we give people instructions to make the best carrot cake as opposed to just the best cake in general? Going back to what we do, we want people to make the best studies for carbon capture utilization technologies, because we want people to be able to compare these different types of technologies. And how do we do this? Well, we provide, as part of the Consistent project, what we call full spectrum guidance on techno-economics and life cycle assessments for CCU. So we provide guidance on commissioning studies. So this helps people that are looking to commission a study ask the right question to be able to answer the question, to ask the right question to ensure that they get the right answers. Because one of the problems here is that we need a discussion between the people that are actually going to sort of conduct the study and the people that want the results of the study, to make sure that everyone's okay with what they expect to see as an output. We have guidance that helps people conduct the studies. So we have guidance on best practices for those conducting studies for a CCU project. And then we have guidance that helps people make conclusions from these studies. So once again, a little bit like the commissioning, a lot of the people that ask for these studies may not necessarily be experts in writing these studies or interpreting the results that come out of those. So our whole project is around helping people get the most out of these studies, to be able to identify technologies that are of best for them. So whether that be they are a policymaker that is looking for sort of a broad spectrum replacement fuel for diesel, for example, then maybe they have specific questions and needs. So they would need to ensure that they get what they want out of the study, is not to waste their time. And to take it back to our example, what we really help people do is ask for the type of cake they want. We help the bakers follow the right recipe and help people judge which cake is best. So when we apply our guidelines, so the version 1.1 we have on the screen up here now, to people's studies, as an example, we can go back to the mix of studies that Lorenzo showed, that Tim showed earlier on methanol. And what we can see is that there's a lot more, when you assess things and only vary the technology as opposed to varying the modeling approach or the background data, all those methodological choices that we've spoken about, we can see a much more consistent picture in terms of output. All of these hydrogenation technologies in blue have roughly the same sort of global warming impact. And the same goes for the solar and the coal electrolysis. So this is great because this now allows us to actually be able to identify which of these technologies is most promising when compared in a more neutral setting. So to give you a few more details on what we do, we specifically address the challenges of using life cycle assessment and technological assessment and TEA for CCU. So we are focused purely on bringing these environmental and economic studies to this carbon capture area. We are currently expanding and improving our guidance documents. So currently we are on version 1.1. We're looking to produce version 2 by April next year. And what our main focus here is to find things that make these studies more useful for people outside of our sort of very small research world. And can we make them quicker for companies? Can we make them cheaper for companies? Because one of the things that's currently sort of limiting is that they're very time intensive, they're very resource intensive. Can we help people make decisions faster by speeding up this process somewhat? Can we integrate the studies together so that we bring the economics and the environmental into one decision-making process and bring these aspects together to be able to make better decisions and to trade off the potential costs with the potential benefits. One of the things that I think is really cool about our project is that this is very much a community-led project. We work closely with researchers from around the globe and other stakeholders, so policymakers and things like this, charities, anyone who wants to be involved really, in making sure that they get the guidance they need and that everyone sort of has voice. We make sure that people can ask the right questions, and we also have guidance on, or we're developing guidance on things like using the right terminology. So there's a lot of disagreement about sort of technical language and how best to communicate this, and can we simplify it and make it more accessible to those outside. We provide practical guidance documents on top of this to help people with sort of step-by-step guides walking through in practical applications. If you'd like to find out more about our project, as we mentioned, we have, I can link you to the website here, Global CO2 Initiative. So this is Volker's zone really. So just quickly to go over the results and take home messages. We need to move away from the linear economy we have currently. And one way to do this would be to start using carbon or start using carbon dioxide creatively and using it as a carbon source and thinking of it in that sense. And through CCU, we can do this. We can use carbon dioxide as a feedstock. We have to be careful how we do it, but ultimately CO2 doesn't have to be the villain in this story. It can also be something that helps us move away from the fossil fuel problem that we currently have. And as we mentioned, we have the tools already to assess these technologies, to help people develop these technologies through finding weaknesses and finding potential benefits and sort of amplifying those and communicating them outside of a very small research initiative that they're in as of now. And our project aims to help these people by help utilize these tools for CCU specifically. We'd like to quickly thank all of our institutions, including our supporting institutions as GCI and Climate Kick for funding us and our research. And we'd like to thank you for your attention. And if we have any time, we'd be happy to take questions. Thank you.
Thank you very much, Stephen. Thanks a lot. So I don't see any open questions. We've been really good with time so far. We try to stay within an hour. I don't see any open questions. There were a few that we answered directly under the question. So if there is any other immediate question from the audience, please feel free to spend the next minutes proposing it to us, and we will try to answer live. I really hope that you all enjoyed our presentation today. We tried to explain the technicalities of our work to a broader audience. So we consider also attendees that don't have expertise in the field. So we hope we didn't go down into too many technical issues, difficult to understand. So I don't see.
Yeah, no, there's a question from Mariam Aboud about other than using CO2 for methanol production, what are the other ways to reuse it? So we've spoken specifically about methanol here just as one example. The answer is anywhere you find carbon, you can pretty much substitute it for CO2, because what we generally do is strip that oxygen back away and either combine it with hydrogen to make fuels or fine chemicals. So we can make a whole range of, we can even make sort of jet fuel and petrol as you recognize it normally. So there are companies like Sunfire in Germany that are doing this. We can make aggregate materials using wastes from steel industry, from the cement industry, and combining those with CO2 to make cements or aggregates. Plastics, so polymers, can also be made using CO2. To go back to, maybe this is the easiest way of giving you So if you can see this actual diagram that you see here covers a lot of the different products that people have already made CO2 or made from CO2. So we can see that liquid fuels, solvents, pharmaceuticals, paints, plastics, everything has potential. there are different roads to them, and sort of currently many of them remain unfeasible economically, but there are a lot of products would be the take home, I'd say.
Stephen, thank you. I don't see any additional questions come in, but I will say that the questions and the comments that we received at the beginning of this webinar really inspire me to think about some follow-on events that we should host to address some of those, answer questions or pick up ideas. And to facilitate the announcements, I have invited everyone to join our mailing list through the Global CO2 Initiative's website. That address is specifically also in the chat. But for now, I want to especially thank you, Lorenzo, Tim, and Stephen, for your presentations. It was wonderful to see and hear how crucial it is for us to change the way how we make many of the products that we need and want. And Stephen, you just emphasized that pretty much anything that contains carbon now can be made with CO2 as a raw material. But we also have learned to make new materials, such as many of the construction materials that currently do not use carbon. So fascinating opportunities. And it is also clear from your presentations and discussions that as we develop technologies, scale them, and bring the products to market, they really must be evaluated for their environmental and economic benefits and risks up front. We cannot afford to make mistakes. It certainly is awful if a lot of people lose a lot of money, but it is catastrophic if we make environmental mistakes. So these assessments will help us to avoid those. And the overview that you've given us today, I think, really paves the road for how these things should be done. So to the audience, I would also like to thank you for joining us, for staying with us, and for the ideas that you have given us. And we hope to see you again in future events. For now, stay safe, stay healthy, and goodbye.